After a quick explainer video there, I think we're ready to jump directly into problems. Critical numbers are simply when the derivative is zero, or doesn't exist, I suppose, but it's often when the number is zero. I'll show you an example, because we've been finding derivatives for, 100 and something videos now. You should be somewhat ready to take on using them for something. So let's start with the first one. I chose some easy ones for problem set number 1. So you can just get a handle on critical numbers. What's f prime of x? You should know the exponent rule by now. We're going to get negative x plus 1/3 here. I think that was pretty clear. And all you have to do to find the critical number, or the max min, or use Fermat's theorem, is all the same thing. So you set this to 0. So since this is negative, I'll just add x over here and we get x equals 1/3. That's the critical number. The critical number is an x value. That's the answer to the first one. Very fast. So you see, sometimes the explainer videos are a nice setup, but we can really use the problems to learn what these critical number things are. You don't have to take it so seriously where you have to understand every little theorem piece that comes through. When you're applying it, it'll start coming to you naturally, just like immersing yourself in another country's language. So what would f prime of x be here? Well, these are all exponent rules again, so we get a 6x squared minus 6x minus 36. What's the next step? Set it to 0. And what's the common factor? We can definitely divide a 6 out. Right, so we get an x squared minus x minus 6 equals 0. Well, that factors. You know your algebra 2 by now, don't you? I didn't. So that'll be an x plus 2 and an x minus 3 equals 0. So either of these can be 0 because a times b equaling 0 means a or b, or both could be 0. So here x would be negative 2 and here x would be 3. These are our two critical numbers. Absolutely no science to it. This is about as basic algebra as it gets. It's just new for you because we're applying it inside the derivative. But just set the derivative to 0. What about the next one? G of t equals t to the 4th plus t cubed plus t squared plus 1. Now I notice something right away. These are all positive numbers. And that's not really a good sign for us. Why would that be? Well, it's going to be hard to make anything with a slope of 0 when everything's positive. Well, let's see what happens. So that would be a 4t cubed plus 3t squared plus 2t. Now that we have the derivative, what do? Set it to 0. Okay, factor a t. Now we have 4t squared plus 3t plus 2. Equals 0. How do we factor this? This isn't a simple factor at all because it's all positives. You know what that means? Quadratic formula. Remember this? Another Algebra 2 concept that you skipped over quickly and thought you'd do fine because you wrote the note card down. The quadratic formula matters. Let's write it out for this. That would be negative 3 plus or minus 9 minus 4 times 4 is 16, times 2 is 32. 16 times 2, yeah, that's 32. All over 2a, that'd be 8. So far, so good. So what are we going to end up with here? Don't forget this t out here. We'll come back to him in a minute, but I want to factor this out. 9 minus 32, we'll get negative 3/8 plus or minus the square root of negative, what is that, 23 over 8? That doesn't feel right, but I'm told I say I feel things too much, so maybe it is. I think it is. So we'll just keep it like this, and we'll say our answers are this guy, t equals 0, and the other would be t equals negative 3/8 plus or minus I rad 23 over 8. And that means it doesn't really exist, and that makes sense because everything here is being positive. If you look at this graph, it's going to look kind of weird, but ultimately it's going to be something like a parabola up, and the axes are going to be here. So maybe this is where t equals 0, right? It'll have a slope of 0 here. We calculated that with this guy who factored out here. But these imaginary zeros mean that they don't exist on the real number scale anyway, so that's what we're going to use here. So the reason that I brought up these simple starting problems for critical numbers is that when you're finding the derivative and setting it to 0, you ultimately want to connect them to maximum and minimum of functions. So I'll give you a quick secondary example if you didn't go into the explainer video here. If I chose something like y equals x cubed, and I took the derivative y prime equals 3x squared, x cubed looks like this. So the only time I can have this be 0, I divide the 3 out, take the square root, you're going to find, of course, x equals 0. And that's kind of at this point here. So I guess if I drew it better, it would look more like this if you zoomed in on it real tight. And that is the only critical number for a lot of these types of functions, is just one answer. But if I have something like a crazy fourth and third function, every single one of these is going to have a slope of 0. So when I find the derivative and factor it out, no matter how many factors there are, every single one of them is going to be a maximum or a minimum. And it's up to you to decide how to utilize that information.